Lab 3 of Physics 1 about black holes. So there are two parts to this lab. In the first one, we're going to find the mass of a black hole using a computational model that generates a black hole of unknown mass with a star of known mass orbiting around it. In part 2, we're going to find the initial velocity needed to escape a planet black hole system using a different computational model, which must be done without crashing into the planet or the black hole. So the concepts we'll be using in this lab are Newton's second law, which is that net force equals change momentum over time, as well as velocity and position update formulas. It's also useful to represent net force in terms of parallel and perpendicular components. This is because the parallel component of net force affects the magnitude of the change in an object's movement, like motion over time, and the perpendicular component is related to the direct change in direction over time. And so the universal law of gravitation is another concept we're going to be using, which is given by this equation right here. So the system that will be in question in the first part of the lab is the star, and we'll see that the star has a gravitational force on it from the black hole, and the black hole also has a gravitational force on it from the star, but because of the system, this is the force we are concerned with. And so the system for the second part of the lab is the spaceship and the planet. So these two things, so there's a force of gravity between the spaceship and planet the planet, spaceship and planet I didn't draw, but there's another force right here, and then there's also the forces of the black hole on the planet and the spaceship, the gravitational forces. So the initial conditions for the code of the first system with the star and the black hole are given here. We also are iterated through the orbit of the star around the black hole, updating the position, velocity, and momentum over time as the star orbited around the black hole. And so we use that to find the net force, and we use the net force to then find the mass of the black hole. And the mass of the black hole that we found was 1.07464 times 10 to the 63rd kilograms. Here's a visualization of that model of the star orbiting around. As you can see, the magnitudes of the force change with relative position to the black hole. So these are also, that was calculated the final net force, the final magnitude of the net force, the final parallel component of the net force, and perpendicular components of the net force. So yeah. Okay. So due to the net gravitational force of the black hole on the star follows an elliptical orbit around the black hole. In this elliptical orbit, the parallel component of net force is stronger when the star is getting closer to the black hole, because gravitational force is proportional to the inverse square of the distance of the two objects. So potential sources of error in the calculation are the accumulation of rounding error that are propagated by the iteration, and also the lack of continuity between relatively large step sizes for changes in time. So the second computational model, initial conditions are given right here. So in the iteration, the position and velocity update formulas, net force equations, and universal gravitation formulas were used to calculate the forces of gravity on the ship and on the planet. And then those forces were used to model the change in position and velocity with respect to time. Once this model was prepared, trial and error was used to calculate the necessary velocity to escape the system. This is a visualization of that velocity and that system. So the velocity initially was negative 2.9 times 10 to the 6th, 5.4 times 10 to the 6th, 0 meters per second. And then the shortest distance that we achieved with the spaceship and the black hole was 5.56 times 10 to the 6 meters. Wow. Okay, so the initial velocity indicates that the spaceship must move up and to the left in order to escape the black hole. The spaceship experiences most gravity when it's closest to the black hole at that shortest distance we mentioned, and it uses that monumental force of gravity at that point to launch itself away from the black hole. Sources of error include rounding error, as the velocity was only troubleshooted to two significant figures, and also propagation of that error because of iteration. So the total net force is equal to the total change momentum over time, and the total change of momentum over time is mass times the change of velocity over time, and the change of velocity over time is just acceleration. So the total net force is actually just equal to force times acceleration. Similarly, The parallel and perpendicular components can be also given by the parallel force, parallel net force, which is the parallel mass times the parallel acceleration, parallel component of acceleration times the mass, and the perpendicular component of net force is the perpendicular component of acceleration times the mass. So if we wanted to orbit around the black hole, the spaceship would need to move down and to the left rather than up and to the left, and have a very high speed in the downward direction and a slightly lower speed in the left direction. As you can see, this is the orbit that would look like, and the initial velocity vector would be negative 4.983 times 10 to the 6th, negative 9 times 10 to the 7th meters per second.